Graphene is a single layer of carbon atoms in a honeycomb lattice. Inside, electrons move at 1,000,000 meters per second, its Fermi velocity. At these speeds, the kinetic energy of the electrons overcomes their natural repulsion, or Coulomb interaction. They zip past each other without interacting. To induce many body phases like high-temperature superconductivity, physicists must slow these electrons down and force them to acknowledge one another. Slowing them down usually requires chemical doping, but adding impurities introduces structural disorder. This clutter masks the specific quantum effects researchers are trying to observe. Solving this requires a shift in strategy, altering the material's geometry rather than its chemistry. The process begins with a van der Waals heterostructure, stacking two distinct two-dimensional sheets of graphene directly on top of one another. By twisting the top layer slightly out of alignment, a new emergent geometry appears. This creates a Moiré superlattice. It is a periodic pattern with a length scale orders of magnitude larger than the individual carbon atoms underneath it. This geometric trick creates a metamaterial, setting the physical stage to rewrite how electrons move. At most twist angles, the stacked sheets behave like a standard metal. Electrons flow through the layers with high conductivity. But at precisely 1.1 degrees, the theoretically predicted magic angle, the graphene's electronic properties collapse and reorganize. These 3D energy pathways, or Dirac cones, perfectly hybridize at the magic angle. The Fermi velocity at these points drops to zero. The steep energy slopes of normal graphene flatten into these flat bands, trapping the electrons and quenching their kinetic energy. By removing the kinetic energy, the 1.1 degree angle flips the balance of power inside the material, leaving it governed and new forces. With kinetic energy gone, the repulsive Coulomb interactions between electrons take over the entire system. Electrons begin to cluster in concentrated circular zones within the Moiré pattern, avoiding the regions between them. This leads to half-filling, the moment two electrons occupy each unit cell of the superlattice. Their mutual repulsion prevents any adjacent particles from moving. This repulsion creates a motte-like insulator. The pristine conductor becomes a quantum traffic jam driven by electron interaction. Researchers proved this interaction-driven phase exists by measuring the material's response without an external magnetic field. This data shows electrical conductance versus carrier density. Panel C reveals deep valleys in conductance at the plus or minus 1.4 marks, which align with the half-filling density. Simultaneously, Panel A shows spikes in energy dissipation and dips in capacitance at those same density thresholds. These synchronized anomalies provide the proof. The pristine conductor is now an interaction-driven insulator. Traditional correlated materials are often locked into complex chemical structures that are difficult to change once the crystal is grown. Magic angle graphene is different. Its electronic states are continuously adjustable using a simple gate voltage. Turning an electrical dial adds or removes electrons, pushing the material in and out of the flat band insulating phase without adding disorder. Twisted bilayer graphene functions as a dynamic quantum sandbox, providing a level of control that static chemical structures cannot match. This tunable system offers a clean pathway to study many body quantum phases that were once theoretical abstractions. Scientists are using this 1.1 degree platform to investigate the mechanics of unconventional superconductors and quantum spin liquids. They are achieving this precise control through the simple geometry of a physical twist, rather than complex chemistry. As engineering continues to target the fundamental laws of materials, the future of physics is hiding in plain sight. Subscribe for more.